So during previous ones, you probably have seen how to construct a data path, right? The flow through an R type, I type, J type instruction, right? So basically, maybe this. What I mean is something like this, right? Where you know the exact components which is being used in each instruction type, right? So this, for example, is for the store word instruction, right? So you realize that store word we'll be using 20 down to 16. Maybe we understand 20 down to 16 in a separate video. But just know that the different components use a different instruction, right? So those components come together to like form the whole architecture for that instruction set, right? We'll look at this one separately, but this is for store word. So these are the components used for store word. These are the components used for any R type instruction, and these are the components used for branch instruction, right? Now, what yeah here is that we also know the instruction specific connection. So you saw the different connections there, right? Now, um, different formats have different data path, right? So for our type, the data path, like the part where the data will take is different. Like when you are considering, and for I type is where it is low store, it is a bit different. Where it is conditional branch is also different, and where is J type is also different. Where we compute the jump target address, right? Maybe we'll do a separate video on that one, but for now, let's dive straight into the single cycle data part. So today we are going to look at the single cycle data pattern. One of its very interesting um, features is that the single cycle data part does everything in one clock cycle, right? So the most computers you have now, right, will separate the things it is doing. It may be fetch, decode, execute, store, write back, like so that in every cycle to do small thing, second cycle to do small thing, third cycle to do small thing, right? Now this is advantageous because it can make you be able to use separate hardware at separate times, right? So for example, we know that when we are dealing with maybe Um, yes, we are dealing with now. Let's consider this whole thing, right? So let's assume that everything was in the blank. So when you are dealing with a full instruction, right? Know that like fetching of the instruction is only like this part which is involved, right? Uh-huh. Decoding is like only like this part, right? Execution is like this part which is involved, right? Then write back and everything. Uh-huh. Now, what this if this one was segregated into that, what it will allow you is that while you are in maybe fetching, right? Someone like while you are in fetching, someone can be in his decoding and will be doing something else, right? While you are in, so it's like whilst you're here, all these hardware are wasted. Nobody is using them, right? Now that's a disadvantage of the single cycle data part, right? Uh-huh. And another thing is that for the single cycle data part, because we are using one cycle for everything, right? We have to duplicate hardware, right? If we were using multi-cycle data path, right? While we are fetching, so that when we are fetching, we can use this same program count, this adder to increase the program counter, right? Now, in decoding, we are not using any adder here, right? Now, in execution, that time the adder will be free, so we could have used that same adder here. We don't need to, how do you call it? Use different ALUs, right? One adder here, another adder here, right? It's a waste of hardware, right? But if it was single cycle, if it was multi-cycle, right, we could use the same hardware for two different cycles because one cycle might not use it, so that previous cycle can use the hardware. The next cycle will be able to use it when it is free, right? We will see the differences, but that's one major advantage of the single cycle and the multi-cycle data part. Yeah, so the single cycle, what it does is that everything is in one big clock cycle, right? So it's like you give the control signals and you make everything rush till they get to the output, right? So you give the control signal and maybe you know the time where the electricity from maybe this point will take to reach this point, right? That's the time you know. So you maybe use that one as your clock cycle. presumably, right? So you know that at the end of that time, the electricity has propagated through. So after they have fought and everything, like there'll be at stable values at that point in time, right? That's the general idea of the single cycle data part. Now, we are going to build the data part iteratively. So we are going to take our time to look at R format, J format, and I format. So there are problems with the single cycle data part, just like I was explaining. And one of them is the CPU time. Remember that the CPU time is equal to what? Instruction count times CPI times cycle time. Do you remember? Yeah. Yes, there's the formula for performance. Very good. Now, remember that the instruction count, right? Whether you are on single cycle data path or multi-cycle data path, so far as you are using the same compiler and the same architecture, it won't change. So this can be assumed as a constant. You get it? Now, the two things which usually change are the CPI and the cycle time. CPI stands for clock cycle per instruction, right? Now, assume that um, this processor is so good because the CPI is one. Do you remember I said the CPI is one from the previous slide? Because you use only one cycle to execute everything, one big clock cycle. So this one processor is so good because the CPI is one. However, if your CPI is one, right, have you talked about your cycle time? So that's one thing we consider. So performance is three things: your CPI, your cycle time, and the instruction counts. Now, maybe you may have a CPI of one, but you have a cycle time of maybe 200 nanoseconds. So it means that your one clock cycle takes 200 nanoseconds. Maybe I have a CPI of four, right? But I'm taking a clock cycle of 50 nanoseconds, right? Now, at the end of the day, we have the same CPU time. We'll take the same time, right? Because 4 times 50 is what? 200. 200 times 1 is equal to 200, right? So it is not a matter of only, so that's why these three things must come into consideration, right? To be able to define the problem correctly, like to be able to define the performance correctly, right? Uh, so we also saw that this one, in order to increase the performance, it is not really a problem of the program because the program is dependent on the instruction count, right? Now the CPI is dependent on the compiler, right? The CPI is dependent on the compiler and the ISC, right? And the cycle time will come from the micro architecture of the hardware. Yes, so that's what you take note of. Now let's start. This is the, should I say, general overview of it. Yes, the single data part, right? So you have a program counter, you have another to increase it by four. I think you have a control part. You have, yes, this one sending signals to the control, but we'll see them into detail. So don't. So data part is based on register transfers to execute instructions. Control causes the right transfers to happen at the right time, right? So let's see the R format data part. Now, we already saw in the previous diagram that for R format, all we need is this one. We just need um, the instruction memory, right? Instruction memory is supposed to be here. Then we need the register file. Then we need the what? ALU, right? Then at the end of the day, we'll write back to the ALU. So for example, if you were right, if here was what? Add R1, R2, R3, like this one, right? It means our operands are what? R2 and R3, right? So yeah, we need the register file to what? Fetch the R2 and R3. Right. Now we need add to select the correct AOU, AOU operation. Then we need the what R1 as our destination register because we'll be writing the results back to what our register file. Right. So you realize that these things, once you conceptualize, like once you know what they do, automatically you know the hardware they involve. Right. So that's the importance of knowing the instructions and knowing the type. Is this an I type instruction? Is this an R type instruction? Is it a J type instruction? So for example, I know that a J type instruction, right, it will not require the, for a single cycle data, it will not require the full ALU, right, to do the computation of the address, right? Now, I also know that for an I type instruction, right, we will not read the second operand from what the read data to, right? And we'll see why later. But once you know the operation of those instructions, right, it is easier to conceptualize and see the hardware which will be involved and the ones which will not be involved. And that's exactly what we saw in this diagram, right? So this diagram was just showing you the hardware which is involved. So the dipping one are more or less like the hardware involved, and the light ones are the ones which will not be involved. So for branch equal instruction, realize that we hardly use all of here, all the um but for something like the arrow type instruction, realize that this is the hardware we use, right? And for something like the store word type instruction, realize that this is the what hardware we use, right? So it's a matter of just knowing what the instruction does. You can conceptualize what the instruction is doing. So what hardware to use. So let's take note. So we've done for the out type instruction. Realize that we just need the register file. They all use, right? And that's all.
So this one equals the data. Let's say I say Anderson. I want to use branch. Let's start.
Yeah. Yeah.
And this one, the only.
Mm.
So from the how do you write it from the other?
How would you write the equation from that?
Like to do the addition.
I don't get you. The ability to be just add R1, comma R2, comma R3. That's the code you write.
But see, you have to write it the you to know that it's doing the
Yeah. So that was control signal. So we'll do that later. Okay. That's control signal. We'll do that later. We just want to see the different hardware. So as you realize that from that one. Now the next one is load store data path. Right? Load store data path. One funny thing is that some of them use quite the same common hardware, right? So here we know that every instruction will be read from the instruction register. That's why we did not draw it here,
Okay.
right? But the instruction register is there. So low store data path as always, they will be read from instruction register, right?
Yeah.
But low store instruction, depending on what is being done, right? What is being done, it may be a bit different. So let's take load word, right? Now the load store instruction, unlike the out type instruction, does not read two registers from the register file.
Yeah.
Sorry, three registers from the register file, right? It only reads two, right? So let me use this one to explain this one, that one. So, for example, when we take into consideration this one, right? Um, when we take into consideration this one, right? Realize that this is the load word instruction, right? And now all the places highlighted in blue are more or less the path it will take. So the blue dash line are the path it will take, right? Now you realize that um we will be using we will be reading from what A2, right? A2 for one of the sources, right? But the second source will be reading from what the sign extended part. Will not be you see that register has two sources, source A and source B, right? But one of the sources, right? One of the sources, like where we write to, where we write the answer to, right? Will come from what? This RD2. Now the first source, which is the base address, will come from what source A, right? And I wish I could duplicate this so that we could see something else. Um, so like that's basically for the load word, right? So for instance, the load word, you know that one of the operands will be taken from source A, another will be taken from source B. However, source B is
Can you write an example like would be
load word. Yeah, so example this one. Load word $3, right, comma, minus 24 into bracket $S4.
Okay.
Right. Now, you see, this thing I've written is assembly code,
Yeah.
right? The computer doesn't understand assembly code, so the compiler will transpile it to machine code, right? Now, the first step in the transpiling process is to put the bits into their correct positions,
Okay.
right? Now, this is the format for this whole box, the boxes, is the format for an I-type instruction. Remember, load word is an I-type instruction. So the opcode will occupy the first 6 bits, right?
Okay.
Now RS occupy 5 bits, IoT will occupy what 5 bits, and the immediate field, right, will occupy the rest, right? Now here the compiler one is transforming into this one. The immediate field will be minus 24, right?
Yeah.
So that's what is stored in the immediate field.
Also.
Yeah, that's the offset. Now IoT, right? IoT will store the destination address, right? Here, the destination address is what? S3.
Yeah. Also.
Yeah, yes, IoT.
Okay.
Right? So the destination address is S3. And I don't think this is different from an out type instruction. Yeah. The destination address is S3, right? Now, if it was an out type instruction, the destination address would have been what? RD, right?
Right.
And the second source of will be stored in RT. The first source of will be stored in RL. But this is a I type instruction. The destination address is stored in RT rather, right? Now, the source operand is what? $S4. This one.
Yeah.
So $S4 in its register value is 20, right? And $S3 its register value is 19, right? So some things you should know. Now you now convert all this to binary, and that's what you see,
Yeah.
right? Then the whole thing here will be converted to what binary of or hexadecimal. So the hexadecimal is below in the binary stuff, right? So that's what it will be fed into the machine, right? So the machine will end up taking the bits and supplying them to the data part, right? So when you see something like, okay, they don't show it here, but when you see something like this, like 25 down to 21, it means what? Bit 25 up to bit 21. Remember, in Mips, usually in Mips, we start labeling 0 from the very first bit.
Yeah.
So this is 0, this is 1, this is 2, this is 3, up to what? 31. It's 31.
Yeah.
Right. So that's what you see. Now, that's also what informs the data part here. So what you see is that um, you have the instruction to be fetched, right? Now bit 25 to 21, right? What does bit 25 to 21 represent in the load word instruction? Bit 25 to 21, right? Um, represents the RS field, right?
Start from here.
Yeah, when you start from 0. So here will be 0 to 16,
Okay.
up to 16, up to 15, sorry, right? The immediate field will be 0 up to 15 to 16 between.
Yeah.
Now from 16 up to 20 will be what? The RT part.
Yeah.
And now from
Please.
21 to what? 25 will be RS. And now from 25 to 38, from 26 to 31 will be what? The opcode, right? Now that's how you review it. So when you see a diagram like that, you should know the bits which are assigned to all of them, right? So for now, you know that here the R, so this is what RS, right?
Yeah.
Now the RS, according to the format, what does it store? The RS is storing what? The base address, right? So the RS is the one storing this one, the base address, right? For store word, for load word, sorry. And the RT is the one storing the destination address, right? And the immediate field is the one storing the what? The offset. Okay. So now when you apply the source address, right, you apply the base address to what? A1, right? So that it will be read in what? RD1, okay, right? And you apply the destination address to um
RD2.
yes, RD2, right?
Yeah.
Because load word is go and pick from memory and come and store it in the register file, right? So you have to also specify which part of the register file should be stored. So and that's the purpose of this one, 20 to 16. Now this one will pick the base address, right? So it picks the base address So the base address, let me represent the BD, and it puts it into the AOU, right? However, it would also pick the um it will also take the instruction. Realize that part of it was what? The offset, and that was from 0 to 50, right? It will also take that one, sign extend it to what? 32 bits, right? And feed it into the what? AOU, right? So now you have the base address here, and you have the 16 bits offset, the 32 bits sign extended offset, right? Fed into the what?
So the stance what does it
The sign extended means that you see that here, let's use here again. Here, here is what? It's not 16 bits.
Yeah.
16 bits. Now, the AOU can only process 32 bits,
Okay.
right? It has to take 32 bits. So sign extension means that we have to pad it with either zeros or ones to make it what? 32 bits.
Okay.
That's sign extension. So this one will take maybe 16 bits, right? So that's why here is small, here is what? Long, right? So to pad it up to what? 32 bits. So if the first bit is 0, it will make 16 zeros small to make it 32 bits. If the first bit is 1, to make 16 ones small to make it 32 bits, right? So that's the sign extension. So it picks the base address, right? It's able to pick the base address. It's able to what? Sign extend the what? Second address. And now we'll use a control signal to select the sign extended one instead of selecting what was read what?
Okay.
RD2, right? So we use the control signal to select what? One. So the control signal will come and select what? This line,
Okay.
right? And now it will add it with the base address. And now to get the address location we are looking for, right? There's the effective address. That's what we call effective address. So after the addition, what you have here is the effective address. Now the effective address goes to memory, right? We are not writing to memory, so memory write is 0. So it reads the data from memory. Then instead of selecting what's here, right? We select because here we'll pick the results directly,
Yeah.
right? For our type.
Yeah.
For load web type at least, we have to choose what? One. So that what you pick the one which is coming from memory, right? So this one will come from memory and now it will be written back, right? But how will it be written back? We have to specify an address here, right? An address here. But the address that will be specified is yeah, the address that will be specified is dependent on the destination we select. Remember, our type was using what? 15 to 11 for the destination.
Okay.
But how do you call it?
Okay.
I type uses 20 to 16 for the destination. Remember, I type will use what? 20 to 16. Uh, yes, like 15 to 20 for the destination, here for the destination register. But our type was using a different type. Let me see if I can find the out. So you realize that our type was using what? 15 to what? 11.
Yeah.
Because here's what? Here's 6 bits.
Yeah.
So 0 to what? 5, right? 6 to what? 6 to 11.
Yeah.
Yeah, I think
16 to 11.
yeah, 6 to 11.
Yeah.
Then 15 to 11 here, like
Yeah.
that. So it's using 15 to 11, right? So it means that the destination or where we want to store is different from I type and our type, right? So that's why we need a multiplexer to select where we want to store, right? And that's the use of this multiplexer. That's the use of this multiplexer actually, right? Sorry, it's not this multiplexer, sorry. Right, so that's the use of that multiplexer. This one is different. So that's the use of this multiplexer. Now, let's continue. So, like you saw, um, those those parts are necessary, right? And in a load or store data path, right, we need this for the following, right? For load word, surely we need this one. We need this one. You know what this one will be used for? AOU will be used for to be used to what? Get the full address. Here's the full effective address. Then we'll know that we'll need to write back. So that's how this line is used for. So when you see the instruction, just have a concept in your mind, like how the instruction will flow. It will also help you to be able to choose the right select signals when you see it in exams, right? Now let's see for a branch instruction. So for a branch instruction, realize that we don't need memory. Here we needed memory.
Yeah.
For a branch instruction, we don't need memory, right?
So, yeah.
Yes. And now for a branch instruction, we need two-way use. Now that's one negative side effect of the single cycle data path. We need two-way use for branch instruction, right? This one would be necessary to check if the two operands, so that in branch instruction, branch I usually equal to branch equal to $S1, $S2. Let's see an example. So branch instructions usually look like this. Be equal dollar two registers to the target, right? That's how they look like, right? And now what this so that's how all branch instructions. You have what two sources, right? And one this one. So these ones will be subtracted from each other, and if they are equal, zero will be accepted, right? And that will be used as part of the control and the data part. This one. So that's the necessity of this one, the zero signal, right? And yes, so that's basically it. You also need this second one for the branch target address evaluation. So you need a PC plus 4, right? And you also need to sign extend the 32-bit um, immediate field. Remember that there's an immediate field here. This target is an address actually. Yeah, we call it the branch target address. It's an address. So when the program is transferred, right, there'll be an address here. Like the program will be, it starts labeling here, maybe 001, right? Maybe zeros. You see that each one is what? 4 bytes, right? Like word, each one is 4 bytes. So maybe here is 001, here will be 004, 4, then 8,
Yes.
12, so that number assigned to this one is what you put here. Right. But we'll see that one separately. But yeah, that's the address we are talking about, and that's what will be taken here. Shifted left by 2, and you add what PC plus 4 to it, right? Yes. So that's basically for this one. So next time then we'll just talk about the R format instructions, how they work.